Okay, we're back, and the topic for this section is going to be on interface design. So we're going from inheritance to interface. We'll see what an interface is and how it's used, and then we'll implement one using source code. I have some examples that I've prepared that I put together so that I don't have to type so much, because I love to type, because I hate typing, I should say. I don't like to type. So I put them on the bhacker.com website, and let me show you where that is, because you're going to want to download these examples because they're showing everything I'm going to go over in the lecture. So they're very helpful, especially if your typing skills aren't so good, or if you don't have a computer with you today, because I do see some people without a computer. You're missing out on some of the lecture stuff without having the ability to actually to work with it right now. But if you go into bhacker.com, go hit on the Spring directory, Spring 2013, Object-Oriented Programming with Java. If you missed the first meeting, or if any of that stuff that I just went over from the first part of this lecture is brand new to you, then you probably want to revisit. This is the live class meetings. Unfortunately, they're not labeled very well. There just goes from 1 to 12 lectures that we went over on 1/20/13. That was a long weekend. So it's all in here. You can revisit the past if you want. The next section underneath it says course materials. In this section you'll see lecture examples. In the lecture examples folder on the bottom you'll see two things that you probably want to download. We're starting here. This is where it says swing examples. As soon as we get done with interfaces and with abstraction, which is going to come next, then we're going to look at swing. That'll be fun stuff. So we're going to hit some core Java programming stuff in the morning. Afternoon, we'll work with building a notepad program, a tic-tac-toe game, work with the GUI parts of it, which is extremely easy. Once you understand interfaces and you understand abstraction and you understand inheritance, it's just a matter of using built-in components, and the swing stuff is actually kind of fun. So we'll be getting to that. But right now what you want to download is this thing called Java Fundamentals. Java Fundamentals is a zip file. In the zip file, if you open it up, load it up into Eclipse, this is all the stuff that's in there. They're all self-contained examples that I'm going to go through. In particular, the one that's called interface point and interface shape are the ones that I'm going to be looking at in this particular lecture. But the directory, if you import it in, is going to have a ton of different separate single standalone examples. So it's not a bad idea to get familiar with the examples. So go ahead and download that, because while I'm talking you can import that into Eclipse. These are some of the projects we're going to be doing. They're Android related because people have an interest in doing this on Android. Once we learn the fundamentals, we're going to apply inheritance, we're going to apply interfaces and all those concepts to Android projects. So it's the same as what we're doing now, but instead of using swing, we'll be on a device. Alright, and this is lecture 5, also coming from the same website, if you're not familiar. So interface design, and let's take a look here what we're looking at as a concept. An interface is a way to describe what classes should do without specifying how they should do it. So it's not a class, but a set of requirements for the class that you want to conform in the interface. If you're in the Objective-C class, you know what an interface is. We have to build them automatically. You have an interface.h, and then you have a .m implementation of it. And if you're not in Objective-C, and if you're familiar with C++, you might be familiar with the concept. It's the header file. Well, is it the header file? It's the .h that goes along with the .c++ when you implement a class. In Java, we just have .java. And we've taken the interface concept and we've separated it out away from the class implementation. So it makes it actually kind of easier, I think, because you may not even hit an interface unless you've actually created one. Interfaces in Java are done in separate classes. Everything is a .java, everything turns into a class, but we have interface classes, just like we have abstract classes, which abstract and interface are two separate concepts. I'm going to cover both of them probably before lunch, see how far we get. Here's an example of one. It's called public interface comparable. What does it do? It compares one object to another object. It's generic behavior. Is it generic behavior? It is kind of sort of generic behavior. Classes that abide by and implement this interface have a method, or have everything in the interface, I should say, implemented, so it contains that functionality. So it's kind of like protocol in Objective-C, if you're familiar with protocols. If you're not, don't worry about it. If you're not familiar with any of those different languages, think of it just like a method that you're going to define as a prototype, but you're not going to implement it. You're going to put it in an interface, and the class is going to implement the interface when it uses it. It can extend and implement at the same time. You can do both. So here's public interface comparable. Comparable says we have an integer compare to method. This is a function prototype or method prototype. There's no opening and closing brackets. This is a method that's declared inside of this class. So we still start with public, but instead of saying class right here, and let's say for example person, this one's called comparable, and this is an interface. So it says public interface comparable. If you go out here to these examples that I was trying to point out, we have two in particular that work together. We have this one here, it's called interface shape. Now I left out the public. Could put public in here, but it's going to be assumed to be public. So actually I'll just modify that so it says public. But it is an interface, and it's called interface shape. I called it interface shape because I have another shape that's going to be used for abstraction. That's an abstract shape. And I put it all in one folder, so I want to make sure the names were unique. So what do we here? We just defined two methods in here. You don't normally see data defined in here. You see methods. So this is a real-life example of an interface. Here it looks just like a class, but we have public double area, public double volume, inside the opening closing bracket, no data. Very simple. Very straightforward. So it requires that any class that implements the comparable interface contains the compare to method. And the method must take an object parameter and return an integer. So it's going to take an object and it returns integer as the data type. So this example out here that we're looking at doesn't take on anything. It just has volume and area. So it's not going to take on anything. Simpler actually. So let's see. So the declaration consists of the keyword interface, its name, and the members. Similar to the classes, interfaces have three types of members. You can have fields in there. We didn't put any, but we can have fields. You can have data members in there. Methods, and you can also put nested classes and interfaces. You can put an interface inside of an interface, or a class inside of the interface. When you do that, you're not subclassing, you're nesting the classes. So the class itself contains another class. Why do you want to do that? For added functionality, and then if it belongs in the same scope, you're going to put it inside the same class. So interface members are the constants. So an interface can define named constants. So up here, as we look at here, we have constant fields. As I said before, we don't normally see data members. The interface is not an object. You can never create an object of a type of an interface. Instead, you implement the interface. So if you can't contain, if it's not an object, why does it have data? It doesn't have data. Instead, it has constant fields or constant information that's going to be used inside of the implementation. And so here's an example. It defines named constants, which are public, static, and final. So those methods are omitted by convention automatically because it's assumed that they're public, static, and final. In fact, that's why we left off the name out here. So this is assumed. You can't have a non-public interface. How are you going to implement it? So you can leave it out, and it's okay. Same thing with the member functions, or excuse me, fields. So all named constants must be initialized. So remember before, and I made a special note to make sure that you were aware of the fact that you never do this in a class. We're talking about interfaces now. You don't ever want to do integer silent equals 0, integer terse equals 1, normal is equal to 2. You want the constructors to set the data, but this isn't a class. This is an interface, so it's a slightly different concept. Because they're constant, it means they don't change. They're final, constant, static. Static means they're available outside of the instances. So static, if you remember, I talked about last time, static means that it's not an instance variable or instance concept, it's a class level. So it's available outside of any implementation of this, which means, you know, as long as you're using it, it's available to the class. It's available to, you know, out in main. So all named constants must be initialized, otherwise you can't initialize them. Especially, you know, you can't get to them. So here we have the 4 little variables. They're all integers. In this particular example, it's interface verbose. It's got 4 different integers on here. And then we have 2 methods, void set verbosity, integer level, and then integer get verbosity. So this is going to, simple example, I'm going to show you one with a shape in a few minutes, but it's just setting and getting information that's set. So interface members, or methods, I should say, member functions. They're implicitly abstract, but that's also admitted by convention. Well, what does abstract mean? So interfaces and abstract classes are very similar in terms of their concepts, so I'm going to explain them sort of both together but give you examples of both separately because they are separate concepts. Abstract is exactly how it sounds. It's not definite, it's not clear, not implemented, it's pretty empty. It's just an idea. I have this abstract concept that I need this method, and the method is going to be called area, or the method is going to be called something. But I don't necessarily know right now what I want to do in terms of the implementation. So you're delaying the implementation till later because the concept exists. You know you want that class to have it, but you don't want it right now. An abstract class is a class. So you say, if I were to make, for example, person abstract, I would never be able to make an instance of person because it doesn't really exist. So it's abstract. So if I had that, and then what we'd extend person, we'd use it. We would use it in employee, like what we did earlier, and we'd use it in teacher, and it would all actually become part of the hierarchy, and it sits as an object, and it is an object. It just doesn't come to life in the earlier stages. It comes to life later on in the hierarchy. We only extend one class and one class at a time. So I should technically, if I wanted to make that class more usable, make it into an interface. If I make it into an interface, interfaces and abstract classes for definitional purposes are practically identical, but they're used for different purposes. You extend one class, you implement as many interfaces as you want. So it gives you multiple inheritance in the language. That's technically, from an extension point of view, it's a single line inheritance. From an interface perspective, when you can extend and implement, you've got multiple line inheritance. What does that mean? Well, you can take a hierarchy of, let's say, vehicles, have a vehicle as a base class, extend the class through normal hierarchies and make it into a boat or a car or a plane. Apply an interface to it and have things to print it out, compare the objects, do sorts of different behavior that can apply to all vehicles perhaps, or all of the same concept. And then things start getting tricky because then people start implementing interfaces that have, like, it's a boat and they're doing stuff for a truck. And then it's like, what is this thing? And then you lose the identity of the object, and all of a sudden things look weird. You say, what is this thing? In Android, you see interfaces constantly. Because you're going to interface something. What is it going to be? Well, you're going to extend a view controller, you're going to implement an interface, and you're going to implement something for some action or some event or some activity that you're going to want to implement. And it means that when you implement the interface, you're including the methods needed. Because in the hierarchy of that implementation, when you include the methods, like when this button gets clicked, because you're going to implement the event listener, and when the button gets clicked, you have an on click. When the button gets clicked, you want this activity to perform. So it's always going to be called on click, because everyone who's implementing the same interface for that action listener is going to be implementing the same method. And so Eclipse will actually help you when you start writing it, because it'll say, you're implementing an interface, but there's no methods. Would you like to implement, then the little question says, would you like to implement all of the interfaces, all the methods that belong to this interface? If you don't implement them, you get in trouble. But you don't have to actually write the code for them immediately. You can just have the empty method bodies show up. We're going to see that, so we'll see what that looks like in action. But in concept, it's not abstract because it is implemented. There is functionality. But because you're following the implementation of this interface, you're required to implement certain functionality that goes along with it to make it abide by the protocol or by the rules of the implementation. So when you write the method, there's other methods that work with that. As an example, on-click listener with an on-click method. When you write the body of that, this is what happens when my button is pressed. And I've put the method, I've told the button to, here, you know, listen to this. I've told the listener to listen for the button. When the method gets invoked, I want you to put a toast message out on the screen or something. I want you to do something. Okay, that's all we have to write. Everything else is in the interface. All the other code for exactly how to respond to that event, you don't want to write that. You don't want to reinvent the wheel. It's already given for you. All those methods are there. It's already implemented. So interfaces can have stuff in them that's implemented. You only have to do the stuff that is required by the interface. Everything else follows through the entire hierarchy. So let's kind of see this in action and sort of see how this works. So in terms of the implementation, they're implicitly public. So they're implicitly meaning that we're not stating this. If we explicitly do it, we're writing some code that says this, and we have an option to change it. Implicit means it's by default. By default, they're all abstract. By default, they're all public, but it's admitted by convention. You don't have to, though. You can put it in. If you saw a few minutes ago, I added it to my interface, and I didn't get a message, an error message. No other types of access modifiers are allowed. If I put private in there, I'm going to have a problem. They can't be final nor static. Interfaces cannot be final because they're meant to be implemented. So if you make it final, the entire interface itself can't be used. So modifiers for interfaces itself, interface can have different modifiers as follows: public, package, or abstract. All interfaces are implicitly abstract, omitted by convention as well. Alright, to implement the interface in a class. 2 steps to make the class implement an interface. So you declare the class extends and implements the given interface by using the implements keyword. So here we don't have to use this with inheritance, by the way. If we said class employee implements comparable, that's actually kind of a good example because then it'll compare one employee with another employee in this particular example. And the comparable methods are going to be, so whatever is in the interface, comparable in those methods, should apply towards all classes. They should work in all classes that are implementing the interface. As an example, if we have vehicle that goes to a boat, to a car, to a truck, it should have to be something like speed would work for everything. So if implemented an interface for functionality, all of those things take gas, maybe, fuel. They all take speed. They would have speed. Maybe they would have, I don't know, maintenance associated with them, and cost associated with them. So think about it as a group of objects all hanging around. What would be common among them? That is put into an interface because you want to use them all together. Interfaces create this kind of identity that they're all abiding by the same hierarchy. Which brings up another question, or brings up another scenario. I talked about inheritance a few seconds ago, and I said, a few minutes ago, I said single line versus multiple line. So in an inheritance, and I didn't look at this, but we probably can later on this afternoon, we start converting objects to other objects. There's a relationship, obviously, between all of the objects of a relationship. In our case, the teacher is a employee, which is a person, which is a object. And it's a single line is a. So then we have multiple lines, right? So we have another one that's a human, or excuse me, animal. And animal has, for example, animal is a base class, and then we have a dog. People are animals too. People, I don't know, other animal types. And then we have inheritance, goes all the way through the line. if we want to make this line over here that comes from human and then this line over here that comes from person, we could stick that all in the same hierarchy and make them all extend from each other. All we have to do is put human below person, and then from the person level add on dog, cat, and all the other animals that come from human. Or we could make our inheritance multiple through the interface and giving them all the same tag or the same ID that says they all belong to the same class. Interfaces bring all of them together from multiple different hierarchies. So if we kept it all separate and said we have one hierarchy that's a chair, sitting devices, and we have a chair, a couch, a sofa, we have all these things that implemented from chair, and we have human over here, we can make human and chair the same by having them all abide by the same interface. So it makes them all the same, gives them a relationship because they're all inherited, or they all obtain implementation from this interface. And maybe the interface is, well, I don't know what's in common with a human and a chair, but going back to the boat, the plane, the car, the vehicles, they all take gas, or they all have a speed. Maybe they all have an engine. Maybe they all have something in common. And then we make them all in common with the interface. So it's a way of bringing the hierarchies together through multiple lines and making them all abide by the same type of protocols environment, which is another reason why this is used. So declare the class that extends to implement the given interface. Here we have class employee implements comparable. And then we can supply a definition for all of the methods in the comparable interface. And the comparable interface might be something where it says an integer compare to, and then we have object another object. And we say, well, what's this other object? Well, we bring it in, we say employee other is equal to employee other object. So let me show you something, and let's go back to, I closed it and saved it so I would have it archived. I'm not going to save this one now. Let's go back and I'm going to show you something. Don't save these examples because then you already have it. So go back to, where did it go? Java review. Okay, I'm like, what did I call it? I called it Java review. And let's go back into our main program out here. And we're going to look at object casting for a second to demonstrate the is a relationship, because it's in this slide actually over here where we said employee other object. Well, we're taking something, an object that's in the same hierarchy or abiding by the same protocol, and we can actually create an interface for this project that we have working right now as well. Maybe we'll do this one. This is a good example. In main here, I have a teacher T. I'll just continue along here. And if your code isn't working for you, by the way, I copied it and I put it on this USB disk. So, and I will also upload it and stick it on the website. So if you want it now, I don't know where the TA is. Here, TA. I'm going to throw this disk to you. If anybody wants the working project that you see on the screen here and you came in late, you didn't get to finish it, ask him. He'll put it, it's a folder, I think I called it Java on that disk. So it's a zip file that says Java review on it, and he'll give it to you. Because sometimes it's helpful to have this in front of you. Alright, so I'm going to take the teacher T. I already have a teacher, it's called T. Well, then I can take and cast, let's say for example, I want a person. And everybody in the hierarchy is the same thing. So I could take this P that I already have created up here and reference them instead of going here. In fact, we don't even have to do this. Here, we can take this out actually temporarily here. We don't really use P for anything, do we? P set name. Let's just reuse P. Here, now, you know what? I won't be lazy. I'll just create another one. Alright, so I'm going to go here, and I'm going to say person another equals, and then I'm going to typecast my employee back to a person. So I'm going to go person from my employee that I already have, which is T. So I took T here and I made him into a person. But T is actually an employee. So if I wanted to right now, see if I okay, so here's the way the hierarchy works. Just to continue with this concept, person doesn't have a person object doesn't have an employee ID, but an employee has an employee ID. So what happens if I took this another person, and then casted this other person to an employee? Well, then I can go back here and say, well, another, I already have the reference, equals employee of T, well, it'd have to be another. I'd have a circular reference. This isn't going to, well, I've taken person, I've casted, and then I printed out, let's say, for example, another dot. Ooh, do I have something to get the ID? Get ID? I think I do, actually. Is it a capital I? I think I did, actually. I think I was... and I'm going to look at the message, and I'm going to say, the method getID is undefined for the type person. Yes, yeah. So, the problem now is that I took another, I translated him into, I took an employee, translated it into a person, and now I'm trying to go back to an employee. And I'm going to have a problem with that because I'm casting in the wrong direction. So a person doesn't have an ID, but an employee has an ID. So we end up with these kinds of different scenarios that we run into when we start casting from one object type to another. But if they're all of the type of the interface, don't have to cast them. They all have the interface capabilities in them. So we can run a comparable. We can run a method. We can treat any object like the same of its other types of objects of other instances from other inheritance lines without having to do any type of weird casting to it like this. This isn't weird. This is actually quite normal. Employee, though, has an NI. So if this was a T, I still have T, by the way. T still exists. So when you work with this, you have to make sure that if you're going to cast an object, the object's only going to have what it is. You're going to treat it like an object. A person doesn't have an employee ID. Employee has an employee ID. So I can take this and I can turn him into a person. Why do I want to do that? Well, maybe I have an array of people. And in my array of people, and you're going to get this in the fourth assignment, in the array of people, or in the array of something that you're going to have, you're going to put all these different types of objects in it. Well, you can easily cast it by creating the array of the particular type. So if I had an array of person, so person, my array, and my array had 10 people in it, then what's wrong with that? Let's take a look here. Syntax error 10, delete by token. Well, let's just do it this way because we haven't assigned anything to it. Is going to be equal to array of 10 people that I'm going to stick in here. Then I can take all of these guys here that I have in this hierarchy, the employee, the teacher, everybody, and I can take that and put it all in here for compatibility reasons by casting it to a person. So I can say, well, it's going to be, you know, item number 1, and my array 0 is going to be equal to person T. My array 1 is going to be equal to person E. And then they would all fit in the array, and then we could pull them all out. But you have to remember that what we're using them for in the array to do some functionality for them, and then we can always go back and treat them. If they were originally an employee, we still have a reference to them as an employee, then we can use that through that reference of them as an employee, we can take them and manipulate those objects. But it depends on what object type that thing is in terms of what you're going to be able to do with it, in terms of running the methods and setting the data. So it was kind of something that I saw in this slide that I didn't point out when I was going through the review. We actually talked, I believe, about object casting, but it was like on the very last hour of the very last day that we were here, so I'm not going to assume anyone remembers anything from that. But that's what's going on here. So in your implementation here, if we were to create this, I don't know if this is going to work or not, but we could try. Well, let's see what we got here. Comparable. This is verbose. I believe in the first slide we have comparable interface. I'm going to cut this out of this PowerPoint here. Or it's PDF file. Let's go ahead and let's go ahead and just add this to our project that we have. So I can say, I'm not going to save this, I'm just going to cancel this here. No save. So I'm back. This should hopefully be my original main, unedited. Very good. So I've got my original project, and don't worry about if you did save that. You just take those lines out, or use it if you want to. Just we're not going to do anything with it. So now I can go File, New, and I can go Class. Is it a class? It is, but it's an interface. And I have one underneath that says Interface. So now I can actually select the interface if I want. If I made it into a class, I can always take the word class and change it to an interface. But I'm just going to head and select Interface. And then it's going to be in the default package. And this one's going to be called Comparable, I believe. Let me just make sure. Comparable. So I'm going to add this interface now. Comparable. Comparable. This is why I don't type. Public. Alright, if I select the default, it's going to give me public. Generate comments. I don't necessarily need it, so I'm just going to press finish. Now I have public interface comparable that I have in here. And comparable is now looking like a regular class, actually, which is going to essentially, add some functionality to it. So I'm going to put this method prototype in this protocol, and this prototype is going to be integer compare2. So I'm going to copy it out of here so I don't have to type it. So now I have edit, paste, oops, delete, edit, paste. Now I have a method in here, and if I save it, I can go save, save it. Nothing's going to happen because I'm not really using it. It's just there. So that's what my interface looks like, and I can take out this keyword public if I want to as well. It doesn't necessarily need to be in here. So let's say I want to compare one object to another. So it's compare to. So take this thing and compare it to something else. So if I have a teacher, an employee, and a person, and I want to compare the objects to see if they're the same, are they the same type? Are they all teachers? Are they all employees? I would run this method, but then I'd have to implement this compare to method in each one of my classes that I was going to use this in. So I can take, for example, let's just look at, it happens to be the next one on the list. Let's take employee. So if the class employee extends person, that's great. If I want it to use this interface, then it's an implementation. So I say implements, and it's going to implement comparable. And I'm going to wait to see what kind of error message I'm going to get. Implements, create class implements, fix setup, put the I-M-E implements, spell it correctly? Okay, very good. But I'm still going to have a problem. The problem's going to be because, hey, we want to put those methods in there. So I'm going to put my mouse over here, and it's just going to say the type employee must implement the inherited abstract method comparable to objects. So I have to put a method in here that's going to match this method here. So I'm going to actually just put the blank one in. I know that there's a way. Let's do it this way. Add unimplemented methods. There's a way of doing it automatically so I don't have to cut and paste it. Or we can make employee abstract. Why do we want to make employee abstract? Well, because employee doesn't implement anything yet. If we made employee abstract, because we have one unimplemented method. So the definition of an abstract class, this can be an abstract class. All we have to do is put a method prototype in there and don't implement it. How do we do that? Well, we implemented comparable and we didn't put it in there. So if we make it abstract, and in fact I'm just going to click on this option here to make it abstract, although this is not what we want to do. Get the keyword abstract in here, the error goes away, everything works just fine. Only problem is we can't make an instance of this object, and we're making one in there. So if I save this change, actually, I'm going to get over here a problem in teacher and a problem in main. Main's going to tell me something about abstract classes. It's going to say cannot instantiate the type employee because an employee is an abstract class. Why can't you make an instance of an abstract class? Because it's not implemented fully. There's something in there that's not implemented. So the compiler is not going to let you make an instance of it. Why do you make an abstract class? Because you want to delay the implementation till later down the road. So And then over here in teacher, I'm going to also have a problem in the teacher class. In the teacher class, I'm going to hover my mouse over and it's going to say something. It's going to say, add unimplemented method, or make type teacher abstract. Because we still haven't done it yet. Because in teacher, well, basically you can't get to the end of the hierarchy as you have in teacher and have something that's not implemented yet. Compiler's not going to let you do that either. So these error messages will go away immediately. If I go back into employee, take out the abstract, edit, undo, make employee abstract. Now I'm in the same boat I was in before, but now I'm going to implement that unimplemented method. So I'm going to add an unimplemented method. If I add the unimplemented method, down in the bottom, I get this interesting override. It's called method overloading, or overwriting, I should say. Well, it's actually overwriting, which is overwriting versus overloading. So let me reiterate that point. We also went over that the first weekend as well. To overload is to complement it, to add more method functionality, to change it, to have both of them available. So we overload constructors because we have the same method that can be run 4 or 5 different ways with different number of parameters. That's overloading. Overwriting, but I like the word write, W-R-I-T-E, instead of ride, because you've overwritten it. It's like taking it and erasing what's on the page and writing something brand new to overwrite or override, which means the same thing, but I don't like the word ride. It's just my own personal preference. This replaces the implementation that didn't exist because there wasn't anything. So when we use abstract classes, we always overwrite. There's no such thing as overloading it because you don't have anything that's completely abstract. When you implement interfaces, you're always overwriting it as well, or overwriting it, because it wasn't implemented. But now this will work if I save the method here. And I've implemented it here, which means teacher got it too. A teacher has this as well, so we can compare the object. However, we might want to overwrite it for the teacher. If we overwrite it for the teacher, then we can compare it with a teacher instead of an employee. Because when we start looking at the implementation, we haven't implemented this method yet, but when we look at the implementation, we're going to compare one object to another to see if it's equal. So when we run the method, then we can kind of see what's going on with it. So let's take a look at the implementation again. It's nice to see it happen. It's boring to look at slides anyway, so let's look at the implementation, see what's going on here. So supply definitions for all methods in the methods in the interface. So here's our public integer compared to object, other object, and that's the method we should have down here, integer, public integer compared to other object. So it's the same implementation that our default gave us, which matched what was in the prototype. Well, we have employees and we have things. I think I'm actually in the employee object as well. So I'm going to actually kind of cut and paste this here. I'm going to copy it actually, I'm sorry. And I'm going to put this code in here. And I am in employee. So this is good. I'm going to paste it down here. And take a look here and see, well, do we have a salary? Well, let's see what's going on here. Let's see what was in that. Actually, this may or may not work. It's actually kind of just an experiment, actually, at this point, to see if it's going to work. We have salary. So I'll put my little thing over here. It says create a local variable salary. Well, from an employee, we didn't get salary until we got teacher. Because salary didn't exist in this example, because this example is slightly different than the one that's in the lecture. So I'm going to take out salary and make this something else. What do we have? ID? ID looks pretty good. So let's take out here, and we can actually go like this and go this.id, which is my preference actually. And then say other ID. Then return -1 if one is smaller than the other, else if this.id is larger than this.id. The meaning of all of this is just really kind of, kind of just for example, explanation purposes. But so this comparable method is taking this employee and comparing it to another employee to see if the IDs match. And we've got an employee other that's created. That's going to be from an object that's going to be sent to it, of any object, and taking the employees. Well, if they're all employees, well, we can do this with teachers. If we have another employee, so we created person, employee, teacher. So now we can go employee, and we can have another one, let's say, for example, janitor, or let's compare teachers with janitors. I don't know. I like that comparison, actually. There's a lot in common. I'm kidding, but staff. We could just make staff as a generic object. And then we compare a staff with an employee, and we can say, well, are you guys, a staff with a teacher, and see if it's the same person or something. So we can compare objects in this particular case to see if the employees match. So, all right, so that's the method implementation that's going to run from the instance of the object that we create that we're going to run this method on. So let's take a look at the implementation a little bit more deep. Yes?
I'm not really sure about what is this object, other object.
Another object is going to be, I'm going to run this one, employee dot, compare, and put in here another instance of another object that I've created, and send it in as an object, and take that object and cast it to another employee so I can do a comparison to see if the IDs match. So we're taking and comparing two objects that are exist. We're going to use this out in main to compare two objects. It compares them to see if they're the same. Well, if the IDs are the same. So we can compare salaries and compare anything. And we're just basically making a comparison, which is why it's called compare, or comparable. It makes the objects comparable. For implementation purposes, it's the way of creating an interface to work with some generic classes that we've created, for an example. So, all right, so class employee implements comparable. We've gotten that far. We've implemented. So we only had one method, so we implemented it. So note, in the comparable interface declaration, the method compare2 is public implicitly, and modifier is omitted. We actually put it in, doesn't really matter. But employee class design, you cannot omit the public modifier, otherwise it will assume to have a package accessibility. Well, we're not going to actually have that problem because we're not using anything outside of a default package. We're not using multiple packages. If we were using multiple packages and we left out public, it's public only to that package, and then it's not going to be public outside of that package. So we're going to have some issues in the visibility. And those are, let me tell you, are probably the worst problems to troubleshoot. Because then you're going to be looking at it and saying, it's in here, it's working, why? And then you're not going to get any particular class is not going to cause a problem. The entire project's going to have this really odd message associated with it, and it won't run because it's not available. Something's not available. So, if a class leaves any method of the interface undefined, we saw this live actually a few minutes ago, the class becomes abstract class and must be declared as abstract. We did that. We selected one of the objects to make it abstract. A single class can implement multiple interfaces, just separate the interfaces by commas. So here we have, as I was mentioning before, we have comparable. If we had a clonable, comma, another interface, comma, another interface, comma, another interface. Multiple interfaces, only one extends. Can't do that with an extend. Only one class extends another class, which is kind of, I think that's kind of weird in the language. Because C++, you can extend multiple classes. Objective-C, you can extend multiple. Anyway, just extend one, implement multiple. So instantiation properties of interfaces. Interfaces are not classes, so we can't make an instance of it. So you never use the new operator to instantiate the interface. So public interface comparable, comparable x is equal to new comparable, not going to work. But you can declare interface variables, comparable x. If we do that, then we can take x and have it equal to something. So remember, this is a reference. We can't use new. There's no such thing as a new comparable. But there's a reference to a comparable that we can do. So making that's okay, but you must refer to an object of a class that implements the interface. X is equal to new employee. So we can do that actually. We can go comparable x. So let's do that actually, because we're going to need to use this anyway. So did I change this? I did. So I'm going to go yes. Comparable. Yes. Okay, so we open up main. And down here on the bottom, depending upon what you got down here, I might actually have to create another teacher or something to compare something further down the road, but let's just make the comparable, and then what are we going to make if I spelled that correctly? Comparable x, we're just going to call it x. Comparable x. And lo and behold, it's going to tell me that x isn't being used. Would you like to delete it? Or something like that? No. Okay. But x could be equal to, and I think we added it on an employee, so x could be equal to, is this going to create a new employee, or are we going to do a new employee? We can do that actually, let's do that. X could be equal to new employee. And hopefully we have the constructor created, we do, for the employee. But we can't create, from here we can't say new comparable, because it's an abstract. Same thing true for abstract classes as well. Same rules actually come. You cannot make an instance of an abstract class. In an abstract class that is being used as a superclass to another class, you may, yes. But you're not making an instance. It's kind of funny. You're making an instance of it. You still get a person. If person was abstract, and we can do this actually, after we get done with interfaces, we'll look at abstraction. We can take person and make it abstract. We just can't do this. It's an abstract class. But we can make an instance of an employee that is a person and treat it like a person and we get a person object. So we get the object, we just don't get it as through the person reference. We get it. We can't make it through the person. We have to make it from the employee because the information for the abstract is incomplete. So it won't let you. The system won't let you make a class that's incomplete. So if you make one further down the road in the hierarchy that does complete it, you can go backwards to a person. You can cast it as a person and it'll work, even though it's abstract. But you made it as an employee, so it filled in the missing implementation, which is kind of like what this is doing. So we can't make an instance of comparable because comparable is incomplete, but employee completed it. So we can treat it like an X actually. So we can cast the employee back to an X and we can make it equal, which is what we're going to see next. So, all right, moving right along. We know that worked because we just did it. Extending, let's see. Yes, we do have some stuff further down the road, so let's see. Extending the interfaces. Extending interfaces, here we go. Extending supports multiple inheritance, yes? Yeah, sure. Nothing's going to happen yet, but run it.
Can you print like stuff that we just did?
What do you mean by print? We just created a referenced object that's of type comparable and called it X. And then we took X and had them equal to new employee. Actually, if we print this out, the constructor for new employee will trigger. So if we did print it, if we did run it, what we should get then as output here is a new employee down at the bottom. So we have in-person default constructor, and then we have in-employee default constructor. But we actually haven't done anything with it yet. We're going to use it in the next couple steps. But we haven't actually done anything with it yet. And I'll make this available as well if you're not copying this down. So some people I see, well, most people are copying it down, so this is good. So you don't have to worry about it. So let's see. So as I was mentioning before, it gives us multiple inheritance. An interface can be extended more than one interface. So super interfaces and sub interfaces exist. So here we have public interface seriable extends Java IO seriable, comma, runnable, comma. So we have the interface itself. That can also be a superclass or a subclass interface to itself, but that example is using extends, which means it's actually inheritance, but should be the word implements, I should say. So an extended interface inherits all of the constants from its super interfaces. So if we put a constant variable in our class comparable, our class comparable isn't going to do anything with constants. It's actually just going to be a method that compares to another one. But if we did, it would be also included, just like regular old inheritance. So inheritance with the interfaces works just like classes. take care of the sub-interfaces, inherits more than one constant with the same name, or to take care of also the situation for or if the sub-interface itself and the super interface contains constants with the same name, always use sufficient enough information to refer to the target constants. That's where this comes into place. If you have multiple same names, which you get actually in interfaces, if you use constants, then you can always refer to the object's name or the object's variable, not that other object's variable. You can also get at the super object. So the this and the super can be used to go up the different levels for the resolution of the value that you're looking for a particular variable. Hardly ever done. At that point it's too convoluted. You'll probably end up changing your design to make it a little bit easier. So let's look at some tedious details here. When an interface inherits two or more constants with the same name, I'm not going to bother doing this instead. We'll just keep them all the same. We'll keep them all different. Or we could put this together if you wanted to, but it's tedious. So in the sub-interface, explicitly use the super interface name to refer to the constants of that interface, a super interface. So here we have interface A, and then inside we have interface B. Interface A has value VAL. This is the problem right here, because we can't, for some strange reason, we've run out of words to use and we want to use the same name. Most people would just use different names to avoid this problem, but let's say you want to use the same name, because then you can just remember what it is, actually. So we have interface. This is the main. This is another one out here. Why it is indented is beyond me. It doesn't need to be indented. This looks like it's part of here, but we have an opening and a closing bracket. It's not part of that. But we just have a constant that's declared. This is a separate one, not inside of this one. This should be moved over to the left-hand side, just for clarification purposes. Interface C extends A and B. And the extends keyword is not implement. As I steered you wrong in the previous slide, this is correct. I was off on a tangent thinking about something else, actually, when I said that. It extends because the interface is extending another interface, just like a class extends another class. In inheritance, we always use extend. So although it's an interface, it's not implementing another interface, it's extending an interface. So that word is proper, the word is extend. If you're creating an interface from another interface, you're inheriting. So one interface is going to inherit another interface. It's extending it. Same with one class that inherits another class, or one abstract class that inherits from another abstract class is always extend. To implement the functionality of the interface, you use the keyword implement. But because these are interfaces, you can extend more than one, which is tricky. I mean, it's convoluted in syntax. I have to agree. I'd have to say that. I'm actually the one saying and not really agreeing. But if you think it's convoluted, I agree with you. It is convoluted because the rules change. You told me I can't extend more than one class. You can't, but you're an interface. You're not a class. But interfaces can extend more than one interface. But classes can't extend more than one class. Otherwise, we get in trouble. But we can extend one class and implement multiple interfaces. And so it's kind of, I didn't write the language. That's one of the people that, actually, if you go online and look at all the gripes on the computer science forums about different programming languages, Java is, it's okay, but it's kind of odd. It has its own particular oddities to it. Here's one of them. Interface C extends A and B system out A dot value, but we have B dot value. So they're class variables, so we don't have to make an instance. They're static, they're final, constants. So we can't change the value, but we can add them together, and in this particular case we're accessing them from the class level. Yes?
So ma'am, like if we use the extend keyword, then we can extend like class along with interface, or
no. Classes can be extended from one class only.
So like if I am using one, suppose D class, so extend D along with two interfaces A and B.
You can say class C, if class C is a class and class B is a class, you can go class C extends class B, comma, or whatever, excuse me, implements, no comma, implements as many interfaces as you want. One class can only extend one class. Interfaces can extend multiple interfaces. That's what I was trying to say. It's convoluted.
So like we can extend class along with interface.
Of course, together, all in one. And that's what we did in this example, actually. In our example out here, if we look at the employee is extending person, and it implements comparable. We can go, what I'm saying here, we can go comma, something else, comma, something else, comma, something else. But if we put it right here, we're going to get a compiler error. But if this were an interface, in fact, in our comparable, we can put extend something else, comma, something else, comma, something else, comma, something else, and we're not going to get a compiler error. It's inconsistent. They got a lack of orthogonality or whatever. And there's many different terms for that. I call it convoluted. It's not really the right word, I guess. Confusing, inconsistent behavior, I guess is. But it's not inconsistent. It's an interface that's extending another couple more interfaces. And an interface concept, it works. It just doesn't work in classes. So. All right, because these are public, static void final, static final constants. A is the interface. A is the interface. We're getting it at the interface level, so we don't have to make instances of anything. We can actually get at the different ones. All right, here's a tedious example number 2. If a super interface and a sub interface contain two constants with the same name, then the one belonging to the super interface is hidden. So in the sub interface, they access the sub interface version constants by directly using its name. The access to the super interface version constant by using the super interface name. So we have here x.value because x is up here. So the dot then is the constant name. So we have y's value and x's value here because we have, now these were separate, by the way. These are two. This is moved out over here. These are A and B. Now we have one inheriting the other. So we have interface x, interface y that extends x. So we have a value here and we have a value here. So we get at the super by specifying the name of the super x, which is what we can do.
Here we don't use these and super keywords, right?
You don't have, no. You're using a dot notation to refer, because you have multiple of the same name. You have to get from multiple interfaces. Specify the interface that you want the name from. Otherwise it's hidden. If I said x here, I'm going to get, the value here is going to be the value only visible in the last implementation of it, because we have technically overloaded it, so we need to go back a level to get the other one, because we have more than one name here, which is overloading, but they're from different areas of the hierarchy. So outside the sub interface and the super interface, you can access both the constants by explicitly giving the interface name. So in the previous example, we'll use a y.value and you can put it in here, y.value, y.x.value. There's no reason why. You don't have to. It's going to assume that it's going to be this one. But you can specify it out just for consistency purposes if you want to. So some of the y and the x to access the value of the interface. Here's another one. So when a super interface and a sub interface contain two constants with the same name, and the class implements the sub interface, so we have them together, and now we have a class that's implementing them. The class inherits the super interface version constants, the last one that was created, as a static field. The access follows the rules of the class's field's access. So if the class has access to it, then it follows those rules. Here we have an example. Class Z that implements Y So inside of the class implementation, we have z.value, which is going to be 2. Z.value, so outside of the class and inside of the class are essentially the same. We're going to preface the interface that it's coming from. So we have z's inside of the class, z's inside of the class, so y is in the interface, so the other one is going to be y. Object reference can be used to access the constants essentially.
But what if class Z implements both X and Y interfaces?
Then we're just going to specify where it's coming from. Is it coming from the interface or is it coming from the class? Or we could use this actually if it's inside of the implementation. Because this is always going to give us this. It's always going to give us our members, data member. So object reference can be used to access the constants. So now we have an object reference to access the constant. Don't worry about all these rules. It's just basically something to think about in terms of the implementation. You can get away with all of this just by using different names. But if you must use the same name value constantly, this is what's going to happen. So it's accessed by using the object reference followed by a dot followed by the constant name. Object reference and the name. So you're just taking it out another level. So these super interface version constants are accessed by explicitly casting. Here we have ZV is equal to new Z. I know it's convoluted. Just say my Z, or Z, class Z is my V, whatever, is new Z. And then we have V.value, Y, V. We want the YV and we want the YV here. And we want the XV here and the XV here. I know, convoluted. That's what I say. Don't be too concerned if this looks like a jigsaw puzzle to you. It is. But you can reference it by the object, then the interface component, then the variable that you're looking at. Or simply use different words. Extending interfaces, so about the methods themselves. A declared method in a sub-interface has the same signature as an inherited method and the same return type. Then the new one is going to override, same thing as I said before. If it's exactly the same, it overrides it or overwrites it. It's going to override it in the method of the super interface. So you can change the method implementation through the interfaces by overwriting them. If the only difference is the return type, then you might get a compile error actually. So the return type's got to be, the same. Otherwise, if you're going to override it, you're going to override it. Make it compile the same way. An interface can inherit more than one method from the same signature and return type. The class can implement different interfaces containing the methods with the same signature and the return type. Overriding in interfaces themselves has no question of ambiguity, so the real behavior is going to be ultimately decided on the implementation of the class. So whatever you put in the class is going to be the final implementation because you're implementing it. The interfaces aren't implemented to begin with, so it doesn't really matter what you're putting in there. The only problem you usually have is with the constants. Yeah?
When we are talking about overriding, and like suppose we created two methods and we have one parameter, one is integer and one is double. And when I'm calling it, is that okay? Will it allow? Because it is.
You can completely override it, yes, as long as the signature matches completely.
Because one is integer, one is double, and since
then you're going to have two. You're going to be overloading it. You're not going to be overriding it. You're going to have both. If it's just for overloading, just for overwriting it, if you're going to use the same signature, you have to return the same thing.
Okay.
Which you're going to have anyway in the method implementation.
Okay.
Most of the time, you're not doing this to overwrite it constantly. You're going to have that one rare exception where you have that one behavior of one method that you're going to want to have it return something else. And you have to, it's a tweak where you have to kind of like figure, well, I have this interface coming from this interface coming from that interface, but we need to change it in order for it to work properly. So it's an exception to everything that you're going to do if you're using these interfaces. Most people aren't going to create their own interfaces. In fact, what you're going to do is implement other people's interfaces. And the interfaces are very common because then it gives basic implementation of things that are going to be following through with other functionality that you're going to get once you implement that method. As an example, the action listener. We don't have to invent the wheel on how to listen on a button. It's already created for us, but the interface is going to give us that on-click method that we need to complete. It's looking for that on-click method. Once we complete that method, then it knows what to do on the button we tell it to listen to. Because it knows on this click, open up this other view. Okay. Or put this toast message out to the screen. That's really what you're using an interface for. But obviously you can create the APIs yourself, and you can create the interfaces. And it's usually part of, when you start using it to begin with, you're usually using other people's implemented interfaces. And that's how you're getting, as an example, some of the data structures to work, which is a very common implementation. We're going to, probably not till after lunch, or maybe not till tomorrow actually, we'll look at built-in interfaces for the Java language for things like linked lists and queues and stacks and stuff. Well, interfaces. You just implement the interface of a queue, so you have the functionality of a in-queue, D-queue, or a stack to pop and push. Don't worry about it if you're a data structures background. This is very simple stuff. We're not going to get into a lot of data structures, but it's used a lot in the data structures, actually, for that. Methods with the same name, but different parameter lists are overloaded. So the method actually is, the overloading on the overriding works the same way as any other method in any other class. So why use interfaces? We have the interface shape. I'm going to show you that in a few minutes, actually. Shape.java class implements with interface point. Subclass of point, maybe circle, cylinder, and test. I have this written for you. I'm going to show these examples to you. Well, parts of it, actually. I don't think I did the circle and the cylinder, but it's okay. Usefulness of the interfaces goes far beyond the simple publishing protocols for other programmers, which is what you're doing. You have the protocol set up for you correctly. Any function can have parameters that are of the interface type. Any object of the class that implements the interface may be passed as an argument because it's all of the same. It's all of the same interface. This is what I called. I didn't call it a marker, but that's what it's a tag. I usually use the word tag. You can tag a class with an interface, and as long as it implements it, it's all of the same kind of class. Even if it's in a different hierarchy, it's tagged. So what do I mean by that? It's a marker. It's a cookie left behind. It says, hey, I'm part of you. I'm part of your group. Even though I'm not really in your hierarchy, but I'm part of you guys, because I implement you too. I implement your interface too. So some people use interfaces for tagging purposes, a marker or tagging. Interfaces, neither methods nor constants. Its only purpose is to allow the use of the instance of in a typing query. Are you an instance of this? Then we know who you are. Clonable interface is such an example. So clonable says you're an instance of this, you're an instance of this. So I can take barb object, and I can make barb1, barb2, barb3, barb4, other objects that are clones of me, and then tag them all with the same interface, even though they're all separate classes, and then they're all the same. All of a sudden, I've tagged them all with the same ID. I can go back, where are all the barbs? And then it was like multiplicity. You guys see that movie, Multiplicity? It's we did, and not this year, a couple years ago when that movie came out, we made a multiplicity C++ program using this. That's why I remember this, actually. I'm not going to do it. It's too boring this time. Plus, half the people haven't seen that movie. Multiplicity, guy duplicates himself because he needs to get more work done. So he clones himself. So in the in the Java version of this, you take and you tag each one of them. They'd all be the same guy, Bob or whatever. And then Bob can, hey Bob, okay, here's Bob. He just had all these clones, so he'd go over and just grab one of the clones. But in the movie, what made the movie good was not all the clones had the same qualities. Some of the clones were stupid. Some of them were slow, or I don't know. Some of them were really intelligent. Some of them were lazy. They had different personalities. They weren't all the same. You just grabbed a Bob at random from the tagging that you did with the clonable interface, and you got a different version of Bob, essentially. So, and then the memory wasn't shared among all the different Bobs either. They're all different Bobs. So So half of them didn't know. Because if you multiply yourself and you have yourself go out and do some work, how are you going to share the information between you? But you can find all the other instances of you out there. So, which is what cloning of objects does. So, anyway, tagging them. If you tag them, you've cloned them, essentially, or you can tag them. So, an object clone. A clone method returns a new object whose initial state is a copy of the current state of the object on which the clone was invoked. So subsequently changes to the new clone object should not affect the state of the original object. It's kind of like pass by value instead of reference in terms of that. But it's not really used in a passing context. It's a cloning context. We just want to make a copy of the object. Well, actually what we can do then is just reference the object if we wanted to by different references. But when we reference the object, different than cloning the object. When we reference an object like I did out there with the T's and the P's for the employee, took the employee, turned it into a person. When we change the reference is getting at memory that has been allocated through new. It's dynamic memory, which means whatever was allocated, we're referencing it with a particular focus. We're getting certain memory that's been referenced, certain memory that's assigned to the person. So we're still working with the same memory. So if we took an employee, casted him to a person, we still have the same memory. It's not a clone. But we have multiple references now to the same memory. So it depends on how you're referencing it as to what you're going to get. Because not all the references are created equal. A person reference is different from an employee reference. It's going to get at different pieces of the memory that's allocated for a person versus an employee, if you catch that. So you have multiple references. It's kind of like linked lists. A bunch of allocated stuff out there and you have multiple references to it. And depending upon how you're referencing that memory, you're going to get different versions at any one moment of time. You're going to get, whatever you're looking at. 3 factors to writing a clonable method if we were going to write one. We're not going to write one for this class, actually. The empty clonable interface, you must implement it to provide a clone method that can be used to clone an object. Clone method is implemented by the object class that performs a simple clone, makes a copy of it. Copies all the fields of the original object to the new object. And the clone not supported exception can be thrown, so it invokes. So here's a little cloning here. We don't actually have copy constructors in Java. We have constructors. We don't have a copy constructor and we don't have a deconstructor like we have in other languages. We don't have to allocate either. We don't have to release. We don't have it because we have the JVM that does it for us. So the Java virtual machine, the runtime environment, same thing on the Android platform, does all of the garbage collection for us. And I have some information on garbage collection for you for this weekend as well. So shallow versus a deep copy. I'm not going to cover this stuff because we're not going to clone. I've decided not to clone because usually when I get into cloning, people get, I lose half the class and it's too close to. You guys are doing okay so far. So I'm going to skip the cloning. But if you're interested in how to clone an object, it's nothing more than constructing a method that makes a copy of the memory that's being allocated for the first object. It makes a new object of the new clone type, copies the old stuff into the new locations, which is kind of simple. It takes this object.id to that object over there, clone.id, and copies this stuff back and forth. So you're actually making what's called a deep copy instead of a shallow copy. Shallow copy of a clone is 2 people with the same. We don't have deep copy people. If we wanted to clone people with a shallow copy, we'd have 2 bodies with the same brain. You'd all have the same memories, the same information, which is what they should have done in multiplicity. If he had made some shallow copies of himself, then they all would have shared everything. Oh yeah, she's coming home at this time. Yeah, I said this to so-and-so. They would all be able to share the same information. So they all would really be one person, but they'd be divided out for different tasks so they can do stuff simultaneously. For a deep copy, it's just like making new people. And then, which is what he did. He made a deep copy. So he had Bob, Mary. I mean, they're different people. They all have the same. In fact, he gave them names. I can't remember what he called them. I can't remember what his name was, but it was like number 1, number 2, number 3, number 4. Which was actually kind of funny because you could tell who it was by the personality, which one was, because they were all different. Although they were all supposed to be the same. So I think was it Tom Hanks or something? I can't remember who's in that movie. The guy won some award for that. Could you imagine trying to play 5 people all in one movie? All 5 different personalities, and you could tell each one of the personalities. I can't remember who that actor was, but whoever that was really good. I think it won some award. This movie was like back about 10 years ago, I think, though. If you haven't seen it, on your DVD list for Netflix or whatever.
We have got a Hindi version.
Multiplicity, huh?
We have got a Hindi version of it.
You have a Hindi version of it? I'm sure it's a popular content. I'm sure that wasn't the original version of it either, so it's probably based on an older movie. But, you know, if you're bored, you might find it interesting and then go back and write some clonable objects and then see in Java, and you'll see what I'm talking about. But back when the movie was like in the movie theaters, it was actually kind of more popular. Anyway, interfaces and abstract classes. Because we're going to skip multiplicity here with clonable. Why bother introducing 2 concepts, the abstract class and the interface? At this point, you're probably wondering why. Why? No, probably not. We have the same thing written here. Abstract class comparable. Class employee extends comparable. Can do the same thing. Public interface comparable. Public class implements comparable. Same thing. A class can only extend a single abstract class, but it can implement as many interfaces as it wants to. And an abstract class can have a partial implementation, which means you can implement some things but not other things. It can also have protected parts. It can also have static methods and so on. It can have all sorts of different things that an interface can't have. In fact, an abstract class has data in it, public data that can be inherited. So if I made person abstract, then I could have a name and an age and everything that would be shared by instances that were created, that would be changeable, that wouldn't be final static, that wouldn't be constant. If I put that same data in an interface, it's constant. It can't be changed. So we want to take data and we want to use it in inheritance, then we make it abstract. If we're really trying to enforce inheritance and build a hierarchy, then we're going to use abstraction and keep it abstract. If we just want to make everybody the same, mark them all with the same ID, or implement the same functions for everybody, then we make it an interface. And let's see, anything else here? Well, the interfaces are limited to public constants. The public methods with no implementation. Yeah. So same thing as I was saying before. So if I come back here just to finish out the employee concept up here, we would run methods. So in the beginning here we have the concept that was given to us. In our implementation, I don't see it here, but we now have a method. Let me just skip this here and just go back to the code here. So in an employee that implemented the comparable interface, we have a method. Now the method that we're going to run in here, because we should just run the method, see what it does, right? It's going to be compared to. So it's going to be the instance of an object dot compared to, and then we're going to put another object. And we're taking it as an object data type. Isn't everything in the Java language an object? Everything is inherited from object. Even though we don't have to explicitly say class person extends object like we do in other languages, it is an object. So if we put a person in here, or if we create another ID, we create another employee and put them in here and give them the same ID, then we're going to end up with the same. So let's go ahead and make some more objects so we can compare the objects and see if they're going to be the same, which is why we put this interface in here. So kind of demonstrates the is-a relationship with objects. Everybody is an object. So we can do this. And we see this a lot with interfaces because you don't know what kind of object you're going to use it with it. Instead, you're just going to make another object of this object. And this object type is going to be an employee. So we'll make our life easy. We'll go to main. And so x is going to be, well, I could just say x actually. X isn't going to match. Don't we have another employee here, E? So we can go here, E dot compare, and then put X in here. And if we do that, we're running the method that's in the employee. And the employee method that we're running is this new one that we got from the interface that we implemented, just like any other method. The demonstrations just show you it just runs like everything else. And so if we compare, I hope this is printing something to the screen. Let me see. it's returning it. So let's put a system out here. So this will system out, and what's it going to system out? It's going to be a -1, a 1, or a 0. So I guess I could have made this a little bit more sophisticated, but what's the match? If it's less than, it's a 0 if it matches. So I don't think it's going to match because I don't know what we set the default ID was. It's checking employee IDs. We created an X which is going to be equal to a new employee. So we created a new employee, we called it X. We have this other employee up here. I set the ID to something up here, 4444. No, that's a social security number. I set 67. So if we run this program right now, we should get a -1, a 1, or a 1. So what do we get here? A 1. We got a 1 out here because, let's take a look here. We got a 1. If this ID is larger than the other ID, this ID for E was what, 0? So we got the wrong functionality? No. The other ID was X, was 0. It is larger because we're comparing E with the other one's 0. So it is larger because we set E to 67. Was that the ID? I don't know what that ID was. But you can see the method works. If we put the same method, so this is why you want to do it. Let me just save myself a little time here. I'll go like this and go copy. Let's put it in teacher. No, let's put it in, well, it's actually already in everybody. It's employee. If I put this thing in person, it would check to see if the social security number was the same. Then we'd know if the person was the same. And it gets inherited just like everything else does. So it's in teacher already, so I should be able to run this from a teacher perspective. I can say, what's the teacher? Because the teacher's employee, right? If I have this right, T. Let's compare teacher with the E, the employee. I know, it's a capital. If I typed correctly. Everything in the hierarchy above employee it works with. Employee all the way above. I should probably move it to person if I want to compare people. Then I could compare, let's say for example I had a person and the person turned into an employee, or an employee was a person. And then we also had a person in here that was, maybe I'm a janitor and a teacher at the same time, and I have another one that says janitor or staff. Actually I am a staff and a teacher because I'm a department chair. So I can be a staff and a teacher at the same time. And then if I'm looking at a course roster, and I can say, which ones of these teachers are also staff people? I can run a compare on the objects to see which ones match, maybe, if I was using it that way, to see which ones are in this list. Or which students. There's a lot of faculty who are students, actually, as well, because some people take classes. So I can look at the students and say, well, which ones of these guys are also faculty? And I can do a compare and see when either that's the same person and the ID matches, if the ID matches a faculty ID or something. But we're going to tag it. I mean, if we tag it, then we can tell which ones of these are from this line, which is where the tagging comes into play. So if I come up here and I put something in here that, for example, that's a piece of data, like, you know, integer my tag, and this equals 100 as an example. I can check for my tag. Everybody that implements comparable is going to have 100. And then I can have another interface. Let's say this one here wasn't called comparable. It was called, I don't know, student or something, a student interface or something. And then I can say, well, from here, which ones of these are also teachers? I can have multiple tags because I can implement multiple interfaces. So I could have an object that had a tag that said my tag was 100. And then I got, maybe even I call it my tag. Let's call this one like, if this was a student object. Student tag is 100. Teacher tag is 100. No tag. Oh, you're not a teacher or a student. So I can tell what the object, if I was using a comparable method as an example, I could tell which object was which which tag that might have included. So I'm going to assume, unless you guys want it, you understand what I'm talking about in terms of those tags. Let me show you another one. So I'm going to leave this one alone. This one has a decent implementation. I'm going to leave this one alone here so I can upload this one. It has the interface in it. Save it. If I go to the Java programming examples that I showed you at the beginning, don't worry, we are going to take lunch soon. If I come down here and I look at the ones that say interface, oh, that's instance of, say interface point and interface shape. So just like the comparable, I have two of them here. I have a public interface shape. I have public double, two methods, no data, area and volume. And then in the point, it implements the shape, interface shape. And in here I have an area and a volume. Same as before. I don't have all this override stuff because I didn't use the automated tools to do it. I just put the methods in here. You just have to put the methods in there and implement them. So people who are in the Objective-C course love this because this is the dot H and this is the dot M. If you're C++, that's the dot H, that's the dot C++. Essentially doing the same thing with this. And this is the interface, yes. So the interface has got the method prototypes. The implementation has the method bodies, match the same as the prototype. In here it's just going to return 0, return 0. We're not really doing anything with it, are we? The point. What's the point of this? It's just showing you the basic format. And so we have X and Y are set to 0 for the point. We have two static data members here. This is the constructor, setting it to 0. We're not really doing anything with this p.print. So that's why I kind of wanted to do something that did something so you can see it. So that's the basic structure. The examples in this directory are very, in this project are very minimal. They're very small. The instance of is kind of an interesting question. If we look at this one here, let me just make sure it's actually implemented correctly. Yes. This is a bad example when it comes to breaking things out. In fact, all of these here are bad examples because they're all enclosed in one file, or most of them are. It's just basically to make it simple for you to look at. You would break this out. We'd have a class vehicle that would end up in a separate file. So I have class vehicle, and this is showing you the instance of relationship. Is this an instance of this object in the hierarchy? Class vehicle, we have string name, and we have a constructor. Obviously, we left out public, private, and protected, and everything on here. So name is equal to vehicle. Class heavy vehicle extends vehicle. Vehicle 2. It's called vehicle 2 because there's another one in here with the same name. It's just for clarification. Heavy vehicle. Here's the constructor name is going to be equal to heavy vehicle. Kind of a interesting way of doing it. Doesn't follow through with what I told you before. If you actually put this, if you put super in here, if you do, because heavy vehicle doesn't own name, vehicle owns name. So don't look at this example for this because this is not what I'd call the best practice, but it does work. You can do this. However, if you do that in here, there's no super. It's all of the same. Super doesn't exist. It actually might work. Actually, it might actually work. But we don't have a constructor up here that's doing it, so it's not going to work. But you can do it this way. You're not using the constructors for your best advantage. Class truck extends heavy vehicle, so we have 3 of them in here. And we're going name is equal to truck. So the name is truck, heavy vehicle, and name is vehicle. And then we have a light vehicle, which extends vehicle 2, light vehicle. So we have another hierarchy, another strand that gets those. So class instance of is just the name of the class, called instance of .java. So we're going to create a Boolean variable, call it result, so we can tell what's going on. The result's going to be true or false, depending upon when it comes back. And now we're going to create some instances of some objects. So here we go here. We have heavy vehicle, excuse me, here's our instance of class, by the way. Calling it instance of, this is the name of the class. In the name of the class, we're actually creating instances of objects. Heavy vehicle, HV is going to equal to heavy vehicle. T for truck, HV2 is going to be equal to null. So in our main method for this driver program, this is why I like my own examples, because this one's kind of convoluted. Result is going to be equal to, and this is what we're looking for in this example, instance of HV instance of heavy vehicle. It actually is going to come out true because HV is a heavy vehicle. So that will come out true. System out, HV is an instance of, and then the result. Could have nested it in there if we wanted to, actually. Result T is an instance of heavy vehicle. T is a truck. I'm not going to come out as a heavy vehicle. HV instance of truck, HV2 instance of heavy vehicle. Heavy vehicle is an instance of, okay, so successful cast from a child to a parent here, or we said HV is equal to T. So we can cast this way as well. We can go equals. So remember before I took an object and I cast it into another object by doing this. So this is what I showed you in the previous example with employee and person. I took an employee and made him into a person by casting him by the ID. This is also another way of casting if it's from within the same hierarchy and you're going from a parent, excuse me, from a child to a parent. You can cast up this way. So if you're going to skip generations, you got to do it this way. You're just going up one level. You could do it this way by using the assignment operator, equals. These guys are object references that were created up here. They're done as a static because we're using them outside of an, we didn't make any instances of the instance of object. So this example is kind of, actually I'd say tricky, but it's kind of loaded with learning objectives. It's showing you static, because we're not making instances of objects. We're just making this. Instead, we made the instances of the objects of these other classes that were in here. And then we're using these instances of the objects from the static level out here just as objects that were created from the class view. Which is why we have the keyword static here. Which is interesting because I've seen some first assignments that have static written all over the place, and I wonder why in the world would a person do that? Because they're looking at an example on the internet that's using static all over the place, because they're doing something like this. Or something, because I'm too lazy to create an instance of this object and put all these objects inside of the object. Or maybe I don't want to do that at all. Maybe I just want to make the instances out here, which I very well could have, and gotten rid of this one completely. Didn't have to do it this way. In fact, I probably should have just made some instances of objects. If I did that, I'd get the same results, however, using the instance of. So if I run this little program here, I should get some output on the bottom that says that HV is a heavy vehicle, comes out true, and the T is a heavy vehicle true, but then we have false and false for the second two because they're both trucks actually. HV2 and HV are trucks, I think, from something up here, yeah. No, T is a truck and HV is equal to T, now a truck. So, well, actually up here, well, no, T was a truck. HV2 is a heavy vehicle, so yeah, it is an instance of heavy vehicle. H2 is a heavy vehicle, false. Do we change HV2 instance of truck? Well, anyway, long story short, it's showing you how to use this syntax. This is the instance of. It comes back and so you can tell, is this object an instance of something else? If it abides by the same interface, it is. So the interfaces are this is how you're going to tag it. So if you tag it with the interface, it is an interface. It is part of this. Actually, this one does come out because of the hierarchy. Heavy vehicle is from vehicle, that's from truck or something, I don't know. One of these has a 3-level. Heavy vehicle is a truck, so it is going to come back true. That's why this one comes back true for a heavy vehicle. So. If you cast them, they're not equal. If you have cast them from, if you took this one here and said that this is HB is now equal to T, you've changed the object identity a little bit, so it may not be equal depending upon what you've casted it to. questions on interfaces. That's what this part was about. Interfaces. We have a little bit. I know it's probably time for a little lunch break. When we come back, I have stuff on abstraction for you. Then we go from abstraction to, I can't remember what else is after that. So then we're almost done with the concepts, actually. Then we can start putting them all together. Tomorrow's going to be all about building projects. I've got some really cool stuff for us to put together. So, but we have to get past the basic examples. So I will upload this, call it interfaces, and then have that available for you. So let me end this video.